Hi, welcome to YouWillUnderstandMath.com. In this video, which is part 3, we will completely derive the definition for the limit using the geometric representation. In part 2, we were analyzing this problem, f of x equals x squared minus 1 all over x minus 1. We were evaluating the limit as x approaches 1, and we found that the limit was 2. As we move in toward this value, and the value happens to be x equals 1, we called this 1 c, and we were looking at the values as x approached c. For example, from the left side of 1 over here, as we approached 1, we noticed that the y values here, the vertical values, were approaching 2. As the x values approached c, or 1, from the right side, we noticed that the outputs, or the y values, were approaching 2 from the top. So the y values were approaching 2 as well. Therefore, we said that the limit of this function as x approached 1 from either the left or the right was 2. We were never concerned with the value of the function at c equals 1, only near it. We got as close as we wanted to c equals 1, but we never evaluated the function at c equals 1. That's the whole key to limits. Consider this interval around c equals 1. If you zoom in, as I've done here, we'll begin at 0.99 and end at 1.01. How far away are these interval boundaries from c equals 1? In order to move from 1 to 1.01, we would move a distance of 0.01. We call that distance delta. Moving from 1 to 0.99 is also a distance 0.01. So this would represent a distance away from c equals 1 by delta units. In order to get from 1 to 1.01, we would have to add 0.01, or delta, to 1. The value of this endpoint of the interval as c plus delta. C plus delta is 1.01. In the same way, we can look at the endpoint of this interval as c minus delta. In the same way as we analyze the interval around the value 2, which happened to be the limit of our function, we noticed that if we move 0.01 below the limit, we arrived at 1.99. If we moved 0.01 units above the limit, we arrived at 2.01. And we call this small distance epsilon. Epsilon is 0.01. Therefore, we could add epsilon to our limit. That is, we could add 0.01 to 2 to get 2.01. This always works. We'll denote this endpoint of the interval by L plus epsilon. In the same way, we can subtract 0.01 from 2 in order to get 1.99. So this endpoint of the interval would be the same as L minus epsilon. Here's a general function, f of x, and notice if we begin right here at this value c, this is an x value, okay? But we're not concerned about the value directly at this c value, but near it. As we approach this value from the left or from the right, we want to know what's going on with the outputs. If they approach some value L, then we say that the limit of f of x is L as x approaches the c value. Once again, it's never necessarily at the value c, but it's approaching the value c. So as x approaches c, then the f of x values are approaching L here. If x is in this interval, if we remember our interval notation, this is precisely the same as looking at this x-axis and this little interval that we've carved out, this open interval, in which we do not include the value c because it could be undefined, as in this image here. We begin at this endpoint of the interval, c minus delta. We move to the right, approaching c. We skip over the value c. That's what is meant by this symbol, the union. And then we pick up right after this value c and continue moving right until we reach the end point of this open interval, c plus delta. If there is always some epsilon value, some small positive number around L, for example, epsilon could be right here. If we add epsilon, we could end up here and here around L. If there's any epsilon, if there's any distance away from L, above L or below L, remember L is the limit. If there's any small distance away from L, and we can find some small distance around C, for which when x is in this small interval, we can also find an f of x value in this interval, then the limit exists and it is L. There is one more thing I want to point out. When we say that f of x is in this interval, some interval from the limit minus epsilon, the limit minus a little bit, up to the limit plus a little bit, we're calling the little bit epsilon. That means that f of x will be bigger than the limit minus epsilon, but it will be smaller than the limit plus epsilon. That looks like this. This is what you will see in the definition to come in just a bit. If f of x is in this interval, L minus epsilon to L plus epsilon, that means that f of x is sandwiched between L minus epsilon and L plus epsilon. It's bigger than L minus epsilon, but it's smaller than L plus epsilon. If x is in this interval, here from c minus delta to c, and then from c to c plus delta, that means that x will always be bigger than c minus delta. It will be smaller than c on one hand, or x could be bigger than c, but smaller than c plus delta. That's what I've written over here. X can be between c minus delta and c, or x could be between c and c plus delta. If it's on the left-hand side, then x will be in this interval, meaning x would be bigger than c minus delta and smaller than c. If it's on the right-hand side, then x would be bigger than c and less than c plus delta. Now we're prepared for the definition. The definition of a limit, the limit of f of x as x approaches c equals L if for every epsilon, remember the tiny number which creates an interval around our limit, there is a delta, which is the small number that creates an interval around our input value c, such that x is in this interval implies that f is in this interval, then the limit is L. I hope you've enjoyed this video. Please give me a like and or subscribe if you've enjoyed this video. Thanks.